fracturing cracked or notched structures. We can distinguish them into two main categories. For what concerns the first category, it basically includes stress-based approaches, both in their punctual or averaged versions. And the second category includes energy approaches, which basically involves some sort of energy balance. On the other hand, the stress and energy condition remain distinct, and generally the fulfillment of one implies the violation of the other one. This is why, more or less 10 years ago, coupled stress and energy approaches were introduced, and one of these approaches was introduced by our research group and named Fine Fracture Mechanics FFM, or coupled fine fracture mechanics. So this is, from a general point of view, how fine fracture mechanics criterion can be written in formula. So the former condition is a stress condition according to which the average stress over a segment of length L must be higher than the tensile strength sigma u of the material. On the other hand, the second condition requires that the integral of the crack driving force related to a crack of length A stemming from the notch root must be greater than a function of the fracture energy. Of course, at failure, the system becomes a system of two equations in two unknown. One is the critical crack advance, LC, and the other one is the failure load, which is implicitly embedded in the function sigma y and g of A. Note that the internal length, the crack advance, L, according to the coupled approach, is no more a material constant, but becomes a structural parameter, thus able to take into account the interaction with the geometry. Note also that a similar criterion, but based on a point-wise stress condition, so just the stress condition is involved, was put forward by Leguillon in 2002. And now let us consider a U-notch. So ρ is the notch root radius, A is the length of a crack stemming from the notch root, and its Y is the frame of reference placed at the notch tip. So this is how basically the fine fracture mechanics criterion can be written. Note that the energy balance now is expressed in terms of the stress intensity factor function K1 of A and the fracture toughness K1C according to the well-known Lewis relationship. Of course, in order to implement the criterion, we need the analytical function, if you want to basically perform an analytical analysis, sigma y and K1. There are no problems for the stress field as long as basically ρ, the notch root radius, is small if compared to the notch to the crack length. We can implement the well-known Krieger and Paris expression proposed in 1967. On the other hand, for what concerns the stress intensity factor function, we can implement this expression which was proposed 2 years ago in one of our work. Note that we propose a more general relationship for blunt V notches, and this is the particular case of U notch, so the notch amplitude in this case is equal to 0 degrees. And this is basically just a picture from our work in 2014. This is the dimensionless stress intensity factor as a function of the dimensionless crack advance. The circles represents the numerical data arising from a finite element analysis. The continuous thick line represents predictions according to our relationship. The dashed line represented the predictions according to Lucas' relationship, which was proposed, to be honest, for elliptical holes, and which was often implemented in the past. And the other two lines represent the asymptotes. I mean, for very long crack advances, the effects of the radius become negligible. On the other hand, for small crack advances, the problem reverts basically to an edge crack subjected to the local peak stress. And finally, after some analytical manipulation, we get this system with two equations. So, starting from the former, once the material properties and the geometry are known, it is possible to solve an implicit equation in LC, so it is possible to get LC, and then substituting this value into the second equation, we get the value of the Big fracture toughness. Here are the two functions f and h involved in two equations, and this integral cannot be solved analytically, so we need some numerical relationship to solve it. Now let us move to the experimental part. So blunt notch samples from 3 different heats of AISI 4340 steels were fabricated on slow bending test in the quenched condition, both from HDA or CTA. You can see there the temperature in Celsius degrees. You can see here the composition of the free steels. A and B steels have a very similar composition. Indeed, the inclusion type and their distribution was different. On the other hand, steel C was further arc vacuum remelted in order to reduce the quantity of P and S, of phosphorus and sulfur. Well, during experiment it was observed that HTA samples all failed by brittle intergranular fracture independently of the notch root radius. On the other hand, basically, CTA samples with a sufficiently large notch root radius show a distinctive fracture path with the formation of a continuous shear lip emanating at some distance from the notch center line, point A in the picture on the left, and then traveling along a logarithmic spiral, point B, you can see the zoom in the picture on the right, to the region of the sample minimum section, point C in the picture on the left. And so, we have 6 different types of steels, free CTA and free HTA. You can see in the second and third columns the material properties, the fracture toughness, and the tensile strength, which were measured during experiments. You can see here the average grain size in the fourth column. Now, in order to implement fine fracture mechanics, we need the value of the tensile strength. On the other hand, while testing plain specimen, it was observed that large plastic deformations were involved. So basically, we neglected the value of sigma u, and we introduced another parameter called sigma 0, which is a fitted strength in terms of fine fracture mechanics predictions. The ratio between sigma 0 and sigma u is more or less lies between 1.5 and 2 for HTA steels and between 3 and 4 for CTA steels. You can see that according to this choice, so by implementing C, this is the value for sigma 0, the critical crack advance, which is not a material constant, so it varies with the radius, this is why there is a range here. Basically, there is a good correspondence between this value and the average grain size. And you can see here the apparent fracture toughness as a function of the square root of the notch root radius for what concerns HTA steels. So in this case, let me say that the predictions are, I don't want to say perfect, but are very good. Also note that it is a dimensionless diagram, so each experimental data has been normalized with respect to its own properties. On the other hand, predictions are less accurate for what concerns CTA steels. You can see here, I mean, the maximum percent deviation is nearly 20%, which can be considered acceptable. On the other hand, it's evident that basically the precision decreases as the notch root radius increases. Our explanation was that, of course, since larger and larger shear lips were observed, basically as rho increases, our linear elastic analysis, of course, loses accuracy. And you can see here, this is just to show you the behavior of the critical distance, which, as I told you before, it becomes a structural parameter, so it depends also on the notch radius. Now, our last step in this work was to compare our predictions with predictions by other models. And for instance, basically, we consider the work by Rich et al. 1976. We invoked, basically, in order to explain the results for HTA and CTA steels, involved the Tethermann's equations. According to Tethermann's equation, the fracture toughness is constant if rho is less than the effective radius, so a specified value of the radius. On the other hand, is a linear function in the square root of rho if the value of rho are higher. Here, sigma f is called microstructural fracture stress, and sigma y is the yield strength. Note that also Rich et al., as well as us, had some problems because, of course, the value of rho f must be somehow basically fitted. And you can see here the picture. These are basically the experimental data carried out by Rich et al. The two straight lines represent Tethermann's equation by implementing the values who Rich reported in his work, and the two lines, the continuous line, these two lines represent fine fracture mechanics predictions. This in order to basically implement a fitted value, a best fitting value. And this in order to have the two Tethermans equations, so the two straight lines as asymptotes in the asymptotic case. So basically it is possible to link sigma 0 with sigma y and sigma f, so the two strengths invoked by the Tetherman and Ricci and co-workers. And so it's time to conclude. Basically, this is just to say that we have considered also quenched and tempered low and low steels. The same consideration as before hold on. I mean, we fitted the value, and there is a good correspondence between the critical crack advance and the average grain size. And this is basically the weak fracture toughness as a function of the square root of the notch of the square root of notch radius. This is predictions for HDAs, so quite good. And this is predictions for CTAs, so good as long as the notch root radius is not so large. Otherwise, the criterion, of course, fails completely. So, to summarize, basically, fine fracture mechanics involves just two material properties, the fracture toughness and the tensile strength sigma u. On the other hand, the latter, the value for sigma u was influenced by large plastic deformations observed during experimental tests, so we decided to fit its value and to name the parameter as sigma 0. Of course, the weak point of the analysis is the physical meaning of sigma 0. And we try basically to give an interpretation to it by combining it with sigma, the yield strength and the microstructural fracture strength invoked by the Tetherman's equation. By implementing sigma 0, FFM prediction on HTA steel samples always going to be accurate. On the other hand, on CTA steel samples, they are accurate below a limit radius. Above it is not reasonable, this is our explanation, to neglect the shear lip formation and the subsequent ductility failure mechanism. Note also, finally, that the length LC reflects basically the dimension of the grain size. So this is the end of my presentation. Thanks for your attention.